In our previous video, we've learned that hydrogen is a gate-level language with fully customizable commands to perform quantum operations. Hydrogen is a Turing-complete language, where the results of mid-circuit measurements can affect the control flow of your program. This means your programs can adapt as they run. In this video, we'll show how to assign inputs and outputs for API requests, assign classical variables, perform arithmetic, use arrays, and use control flow to condition the execution of your commands on runtime variables such as measurement outcomes. To assign or retrieve variables via API requests, you can use the input and output keywords, respectively. The input keyword allows you to pass values to a variable, and the output keyword allows you to receive values from variables via an API request. You assign the input keyword to a variable, and its value is defined in the body of the API request when the API that executes the program is called. In this example, we assign the input keyword to a variable a. The value of a sets the rotation angle of an Rx gate that we apply to a qubit whose address is variable b. You can use output to return variables and results from anywhere in the program, available as an API request. In this example, we initialize, transform, measure a qubit, and return the measurement result as the output. First, we create a qubit in state 0 and store it in the variable q. Then, we apply a hardware-agnostic command preparing the qubit in a superposition. We measure the qubit in q and store the classical outcome in variable a, which will be returned to the user using the output keyword. We note that several variables can reference the same qubit. In this example, we create a new qubit and assign it to the variable q. We then assign q to q-alias. Both variables now reference the same qubit. Numerical values can also serve as directly defined input to the program. Here, the value of variable a is directly set to 1. For arithmetic expressions, you simply write down your computation using numerical values and operators. For example, a is assigned a numeric value of 2. You can also perform multiple arithmetic operations in line and conduct arithmetic on declared numeric variables. Hydrogen also supports arrays. Each element of an array acts as a variable in its own right, and each element must be the same type of variable, which is either a numeric value or a subsystem address. Here, we create a quantum subsystem with the qubit command and store it in an address at index 1 in the array. Arrays in triple alpha are sparsely indexed, meaning you can assign arrays elements with any non-negative index. In order to perform control flow in the hydrogen program, we use control flow blocks. Here is the general form for each code block. To open a code block, you specify the block name, followed by its successor blocks. A program run begins with the start block. To end a code block, you can use one of either the keywords advance, branch, or halt. The advance keyword closes a block and proceeds to its single successor block. Here, block A is the successor block, so the execution proceeds to block B. The branch keyword closes a block and proceeds to one of several possible successor blocks. The successor is chosen based on the value of a classical variable. The value acts as an index into the list of successor blocks, starting from 0. You declare one successor block for each possible value of the variable. Here, block C and block D are the possible successor blocks. In this case, if mesh 1 is 0, execution proceeds to block C, whereas if mesh 1 is 1, execution proceeds to block D. The halt keyword terminates the program. This quantum teleportation example illustrates how control flow blocks in hydrogen can execute certain sections of code depending on the value of the variables. In the next video, we'll learn about helium, our basic-like programming language that is the next level of abstraction above hydrogen.